Hello everyone, my name is Sebastian Weiss and I will present our work Volumetric Isosurface Rendering with Deep Learning Based Super Resolution, published at TVCG 2019. The basic idea is to start with a low resolution rendering of an isosurface. A neural network takes this image and upscales it to a high resolution image with additional shading information. But why do we care? Why do we use a neural network when we can simply render the high-resolution image? The answer is that rendering is not for free. The rendering time roughly scales linearly with the resolution of the datasets. While a low-resolution rendering is cheap to compute, at a high resolution of, for example, 512 to the cube, it already becomes challenging to have real-time performance. Using a low-resolution image in screen space reduces the rendering time. And a neural network for upscaling has a performance cost that is independent of the volume resolution. Therefore, for large datasets, we see a point where it becomes more efficient to use a super resolution network instead of rendering the full resolution. The downside is, of course, that the network results in an approximation and introduces errors. Therefore, we see applications mostly for interactive exploration and foveated rendering tasks, where slight errors are acceptable. The proposed network builds upon several related works. Here we summarize the most important of those. For single image super resolution, Wenceshi et al. Are among the first to propose a network architecture that is capable of real-time super resolution. Sachadi et al. Proposed EnhancedNet, a high-quality and fast network architecture. The network architecture is also used in our work. For video super resolution, the follow-up paper from Sachadi et al. Introduces a way to improve the temporal consistency of the predictions. Nalbach et al. Proposed deep shading, where a neural network is learned to infer the final color and advanced rendering effects like ambient occlusion from deferred shading buffers. We build upon that idea that our network also estimates ambient occlusion. Next, we provide an overview of our processing pipeline. First, a low-resolution rendering of the isosurface is performed. Note that we use the mask, storing if the ray hit the surface or not, the surface normal, and the depth as input. Not the shaded color image, as using color instead of normal depth decreases the quality of the reconstruction. The mask, normal, and depth maps are then passed to the super resolution network. It produces high resolution images of those. A fixed differentiable screen space shading is then used to assemble the final color image. Additional to the mask, normal, and depth, the network can also learn to estimate ambient occlusion, similar to deep shading by Nalbach et al. This greatly improves the visual quality without sacrificing any performance. If applied to animated sequences, the proposed method up to now leads to severe flickering artifacts, introduced by the lack of temporal consistency. This is because each frame is completely processed independently of the other frames. Sachadi et al. Introduced a way to improve the temporal consistency, as shown here. The output of the previous frame is warped by the optical flow and then used as additional input to the network. The optical flow can be directly extracted during ray tracing. Together with a loss on the temporal consistency, this greatly decreases high-frequent flickering in the animations. The network was trained on images of ejector, that's the dataset shown here as well. For a quantitative analysis of different loss functions and several image metrics on validation data, we refer to the paper. Here, as an example of the evaluation, we analyze if we can give bounds on the maximal error introduced by the network. If we look at those two images, on the left the super resolution and on the right the ground truth, they are almost visually indistinguishable. But if we take the difference of those images and scale them, errors become visible, especially among the silhouettes. To get empirical bounds on the error on the validation data, we can look at the cumulative accuracy. These plots are also called REC curves, and at the x-axis the allowed error is plotted. Along the y-axis is the percentage of pixels that fulfill this desired error bound. If you look at the color, for example, our proposed network in blue sadly only reaches 100% of pixels at an error of 1.0, meaning there will always be an error in the predictions. But if you compare to the baseline methods like bilinear or bicubic interpolation, the network always outperforms those. Meaning the baseline also always introduces errors and always have less pixels within a desired error bound. This already shows that the network at least can't be worse than regular interpolation on the validation data. For further quantitative evaluations, we refer to our paper. Next, we demonstrate that the super-resolution network can generalize to novel datasets that were never seen during training. First, a CT scan of a human skull at resolution 256 to the cube is shown. From the low-resolution input, the network can predict a high-resolution version. The quality is comparable to the ground truth. Next, a CT scan of a human thorax is shown. This is an especially difficult dataset as the high-frequent details or noise in the stomach region are very challenging for the network. One can see that the network fails to predict the high-frequent details in a temporal stable way. Finally, a Richtmeier-Meshkov dataset at a resolution of 1024 to the cube is used. It shows many fine details and larger concavities. The super-resolution network can accurately reconstruct the high-resolution image with ambient occlusion in this case. Here you see the ground truth for comparison. Next, we highlight two example applications. First, for interactive exploration, rendering the full resolution dataset is often too slow for an interactive experience. The two most common solutions are to reduce the volume resolution, which leads to massive loss of details, or to reduce the screen resolution, which results in flickering due to undersampling. Here, the proposed method helps by upscaling the image to the full resolution. And then after the camera movement stops, the image generated by the network can then be replaced by the ground truth rendering again. As a second example application, we demonstrate how the proposed method can be used in a forwarded rendering. Here, a full resolution rendering is only used in the focus region, shown under the mouse cursor. In the vicinity, only a low resolution rendering is used. If the focus region is moved around, one can see a transition from the low to the high resolution image. Now when the network is used in the vicinity instead, the differences are much less noticeable. This is advantageous as it is less distracting for a human observer. In the focus region, the full resolution rendering without any error is still used. To conclude, we presented a super resolution framework that takes low resolution renderings of isosurfaces and upscales them to high resolution images. The network also generalizes well to novel datasets without the need for retraining. And we've shown that it can outperform high resolution rendering on large datasets, even though the network itself has quite some high constant cost. We see possible applications mostly in the field of interactive exploration tasks and forwarded renderings, where hard real-time frame rates are desired and small errors in accuracy can be neglected. For future work, we would like to extend the approach to direct volume renderings, and furthermore, the method currently only works with a fixed super resolution factor of 4 times. Instead, we would like to use a form of adaptive sampling, where more samples are taken in more important regions. For a first step into that direction, we refer to our follow-up paper on arXiv, Learning Adaptive Sampling and Reconstruction for Volume Visualization. In this work, a first network learns an importance map, which is then used to select the locations for the sparse samples. A second network then reconstructs the final image. This whole pipeline can be trained end to end. The source code is available at the link below. Thank you for your attention, and I'm happy to answer any questions.